So this is going to be a fairly short block in which I just try to show you how having more data per observation can be helpful in improving statistical power. So I'm going to go straight to this script, which is called simulating items. So I'll come out of PowerPoint and go straight to my R screen. So this is, I'll just clear this and this. So always begin with a sort of nice, clear everything. And this is, again, my scripts are not terribly well written. You may have noticed that if you are an R expert. They're designed really to be easy to follow. I hope that, they're relatively straightforward to work out what's going on. And this one is just, it's fairly clunky at several levels, but the idea is to try and simulate a situation where you might be measuring blood pressure in a group of people, half of whom have had a placebo, half of whom have had a blood pressure lowering drug. And when you think about variation in those results, you could have variability that is just down to the fact that some people have resting blood pressure much higher than others anyway, but you also have got the fluctuations within people. Blood pressure is quite a nice variable to think about that way because it can go up and down quite markedly in some individuals, or perhaps in all of us, depending on what you're doing. So what you're trying to do in this simulation is focus on variation, a situation where most of the variation might actually be moment by moment. So that might not be terribly realistic, but it's useful to illustrate the point I want to make. So we're going to say we've got 50 people, and this is the variance in the population from person to person in their overall stable blood pressure, if there was such a thing. We'll call that the true blood pressure, which is the individually determined. And so we can simulate that just as we've simulated many other things. So we've got a true blood pressure variable, but we're also going to then simulate the fact that people might vary around that estimate of their true blood pressure. And this standard deviation is made bigger to illustrate that. And as I say, this is perhaps not the most realistic demonstration, but it helps demonstrate the point I want to make. But we can play with those values. You can see how it affects things. So I'm going to put that into a data frame and add a group variable where the first half of people are in group 1 and the second half in group 2. And we can look at it here. And here we are. We've got our true blood pressure and we've got groups 1 and 2. So that's all looking as it should do. When I program, I'm always looking at things from the environment pane just to check what I'm doing. And that it's a good way of checking that things are coming out as you expect. And we're going to say the effect size of the drug is 0.3, so that's actually quite big. It's really going to drop people's blood pressure by an amount that is quite significant. And we will then say we can have another variable, which is going to be their treated blood pressure, which for people who are in the placebo group will be the same as true, and for other people it will be 0.3 less. So here we are. This is now just this value with 0.3 taken off for people in group 1. People in group 2, it hasn't changed at all because they haven't had the treatment. Right, so now we want 5 observations of blood pressure from each person. And this time we're going to be sampling from a distribution for each person that has their own treated blood pressure as a mean, and then this variation around it, allowing you to get different estimates on different occasions. This is just creating 5 columns to hold those values with null results in them. NA is not a number. This is just, I could just put, C index is just a way of finding what's the columns that we have to write our new values into. This is going to be the column corresponding to the first of these. The reason I'm actually finding it out this way, I'm actually saying of all the column names, which one corresponds to O1 is because that's a much safer way of programming than to hard code it. I could just put C index equals 4 because I know it is number 4. But if I were then to put some different columns into my sheet or start trying to cannibalize this script for some other use where it wasn't the 4th column, I'd run into difficulties. So this is a good way of doing it. But we then, for each person, so this is going through a little loop, for each person, each row of this thing here. We're going to take this as the mean and this value of ind SD as a standard deviation and fill these up with 5 different random numbers created that way. So this is what happens here. So here you see we've got 5 numbers. The mean is this treated value for that row, and then the SD is always the same. So now we should be seeing that we've got values in here. And we can then say, well, we might want to compare 2 groups on just one of these measures. The first one, it could be any of the 5, but we'll take the first one. Or we could take an average of 3 of them, which is just you take the row means for the columns beginning with 01 and going on to 2 further columns. So that's columns 01 to 03. Or you can take an average of all 5. So this is just taking averages of either just 1 or 3 or 5. And you get a t value for each one. And we can have a sneak preview of those. I don't know what they're going to look like because it's different on every run, but we've got t of we've got no evidence of a group difference if we take just the single one in this case. Let's try my t3. And now we've got actually a significant p-value of 0.03. So that's showing you that is actually looking more promising. And if we take my t5, then you've got a highly significant difference. It doesn't, as we shall see, it doesn't always come out quite as dramatically as this, but it's really, I want to plot the data so you can understand why these are looking rather different depending on which data we're using. And to do that, I have to have a bit of a digression and put the data in a different format, what's called long form data, which means that you actually stack these different variables on top of each other if you want to compare them. And there are very good ways of doing that using other aspects of R, but I'm going to do it in a very transparent but clunky way. So I'm going to make 3 chunks, all BPA, and in each one, so this one is just taking column 01 and it's renaming it BP. And I'm creating another column called measures, which in this case is 1 measure. And then I'm going to make another little chunk for the column that has the average of 3 measures in it. So I'll just show you all BPB looks like that. So it's now got 3 documenting how many measures have contributed to that value, but otherwise it's just picking up these other columns. And then we're doing the same with 5. And then I'm going to just bind them all together. So this R-bind binds rows together. So I've got everything, all these little chunks now stacked on top of each other. And so I've got 300 observations instead of 100, because for each subject there's measures 1, then there's measures 3, then there's measures 5. Okay, so and now I can make a text that corresponds to telling us what the different values of t and the associated p values are for each condition. And then finally I can plot it. Make perhaps the plot screen a little bit bigger so you can see it. But what you can see is that these different p-values that you got, depending on how many variables you were using, do get more extreme, but this also gives you some insight into why. The variance is much greater if you've just got a single value. If you've taken a mean of 3 values, it comes in. If you take a mean of 5, it comes in yet more. I'll run this whole script just a couple more times just to show you how this will vary. This was just a single simulation. So again, this time, actually, the first 2 don't come out as significant, but the third one does. And this one is not dissimilar to the previous one. So you can play with this and you'll see it varies from time to time. Of course, I do realize that many people would say we should not be interested in p-values at all. Why am I saying how many are significant? And there is a case to be made for saying that that is a rather oversimplified way of thinking about things. But at least it means that you can see how p-values do change, even with exactly the same simulation. Things come and go. But the point I wanted to emphasize here is that if you're using measures that have a lot of variance in them, you'll be less likely to see an effect. And if you've got a measure that's based on the average of 3 observations or the average of 5 observations, you're more likely to see the effect. So let me just go back to my PowerPoint here, and this takes you through the script, but we can go on here. So the basic point here, if you repeatedly run the script, you'll see that usually the chances of obtaining a p-value below 0.05, that should say, will increase with the number of measures that are averaged. And that's because the estimate is less noisy. Also, the average from several measures will be closer to that true value that we use to generate the measures. The pattern results will depend on how much variability is actually due to stable individual differences, that POP-var value, and how much is due to fluctuations within people. I cheated a bit by making that a lot bigger, that IND-SD, than POP-var, which pretty well guarantees that you'll see this sort of pattern of results. But you should play around with them to see how they influence results. The other point to make is that I've focused just on random error, but it's also important to be aware of systematic error. So it's not necessarily always a good thing to get more and more data, because you might then get changes in what you're observing, which are more systematic. So you might, for example, if you're measuring memory or something, you might start seeing habituation effects. You might start seeing effects as people become less anxious or more bored. So if you are increasing the number of observations, it's important to take into account the possibility that those sorts of effects might occur. But for the moment, I'd just encourage you to play with that script a bit and to get more of a sense of how it works. And if you have questions, write them down and save them up, and we can deal with them on an interactive session. But for the moment, we'll stop sharing, and that's it.